Good morning. All right, I guess I'll go ahead and get started. Why is that so dark? Like, you see, here's my hand. Here's my hand. Here's what's going on here. All right, I'm going to turn off this camera and turn it back on again. Office hours is from 2:10 to 3 today. I just sent a remind message about that. Okay, let's see if this is working better now. There we go. 1, 2, 3, 6. Okay. So we have a couple of things to talk about today. The first thing I'm going to discuss is something called current density. All right. So current density is denoted by J. And if we think about a wire, for example, most wires have a circular cross section. And the wire has a total amount of current flowing down it. But that current might not be distributed evenly throughout the wire. Okay? So, you could have a situation. So I'm going to imagine taking the cross section of the wire and then rotating it so that it looks like a circle. So you could have something where you have like a uniform density of current so that the current is evenly spread throughout the cross section of the wire. You could have something where you have more current in the center of the wire. Okay, and it kind of gradually goes to 0 as you get further away. Something like that. Or you could have the reverse of that. You could have something where you could have more current on the outside. Or you could have, current on one side of the wire only. I don't know. So there are all kinds of different, that would be current is only flowing down one side of the wire. So this is what the current density is describing. It's the current flowing divided by the cross-sectional area. Okay, So it is basically written as di d area, current per area. And so this would be the case of a constant current density, because no matter where you are within the wire, you're getting the same amount of current. Here you have more current in the center. Here you have more current on one side than the other. So these would be non-uniform current densities. And this one would be uniform. All right, so I think it's fairly obvious that the units of current density would be units of current divided by units of area. So that's going to be amps per square meter. All right. So what if, so let's just do a couple of examples pertaining to current density. What if you have a circular wire of radius r, big R I should say, all right, carrying current I uniformly. Okay, so what is the current density in that case? Well, you have a certain total amount of current, okay, and then the cross-sectional area of the wire is pi r squared, because it's a circular cross-section. So this would be the current density, and it would be a constant because it is a uniform distribution of current. Okay, so then what if I ask the question, well, how much of the current is within a radius little r? So if we think about it, if we think about this wire, let's just imagine looking at the cross section of the wire. The wire has a radius of big R, okay, and we want to know how much of the current we know is spread evenly throughout, okay, but what we want to know is how much is within this region that has a radius of little r, okay? And so if you have a situation where the current density is uniform, well, your current density is just current per area, all right? So if we take both sides and we multiply by area, all right, we would get J dA equals di. So we know that the current density is I over pi times big R squared. And then what we have to ask ourselves is how much area is in this inner region? And that should tell us the amount of current. So that amount of current, or that amount of area, is pi times little r squared. So current density times the area is the amount of current that's passing through that area. So the pi's cancel out, and we get total current times little r squared over big R squared would be the amount of current that is within this distance from the center. How do we deal with non-uniform current densities? So a wire has, let's say, J of R equals a constant times R to the 4th power. So what that means is that the amount of current that is in the wire is growing as you go towards the edge of the wire, right? Because R to the 4th is an increasing function. So you get closer to the edge and there's more and more density of current. So most of the current is on the outside edge of the wire. The wire has radius big R. How much current? In total is the wire carrying? Okay. All right, so how much current is in total is the wire carrying? Well, we know that from this discussion right here, we know that dI equals J dA. All right. The area, because we're talking about wires of circular cross-section, the area is going to be pi times R squared. So that means that the derivative of the area with respect to R is going to be 2 pi R. And then we multiply both sides by dr. And we get dA equals 2 pi R dr. So that is what I'm going to plug in right here. Okay, so I have J times 2 pi R dr. And now, if I want to actually solve for the current, I have to integrate both sides to get rid of the differential d. So what that means is that the total amount of current is going to be the integral of J times 2 pi R dr. So this is actually an important equation for today. And that's with a circular cross-section wire. So we have the area is written like this. So in this particular problem, J is C times R to the 4th. Okay, and we know that the wire has a radius of big R. So so basically my integral is going to be from radius 0 to radius big R. Okay, so factoring out everything that does not depend on little r, our integration variable, gives us 2 pi c, integral from 0 to big R, of r to the 5th dr. So this r to the 4th multiplies with this r. Okay, and this gives us an integral of 2 pi c big R to the 6th over 6. So that would be our answer. for the total amount of current that's carried by that wire. I'm going to focus this. All right. So the next thing I want to talk about is something called Amperian loops. Okay. So an Amperian loop is like a lasso. Okay. Think about it like a lasso. And it has a direction. So there's a direction, and that's like the direction that you're walking around the loop, if you will. And so when we have an Amperian loop, there's going to be a convention for positive and a convention for negative. So how do we determine the positive direction of an Amperian loop? We use the right-hand rule, okay? So what I do is I put my thumb in the direction of the current flow, okay? Or it's not current, but the thumb in the direction of the lasso flow, if you will. And then the way that my fingers curl define the positive sense through the loop. Okay, so I take my right hand, put my thumb in the direction of the flow around the loop, and then you can see that my fingers are curling out of the page. So basically, for this loop, out of the page equals positive, and into the page is negative. Okay? All right. So the thing about Amperian loops, enclose current. Okay? So what if I have this Amperian loop, and what if I have a number of currents? So I have this current, and that current is a dot, so that's an out of the page current. Okay, so this is 5 amps. This is 2 amps. Here's an X, so that is a current into the page. Let's say that is 20 amps. And then there's a dot here that is 4 amps. And then there's an X here that is 90 amps. So we would say that the current enclosed, I sub enclosed, so we don't care about the currents that are outside the lasso. Okay? We only care about the currents that actually pass through the Amperian loop. And so these 3 are the ones that pass through the Amperian loop. And then we count them according to the sign convention here. So what that means is that because of the right-hand rule, we determine that out of the page is positive. So these 2 amps and 5 amps are positive out of the page, so plus 7. And then the 20 amps is into the page, so we have minus 20. And so that gives us minus 13 amps is the current enclosed by that Amperian loop. Okay? For example, what if we had an Amperian loop that was like this. That Amperian loop is enclosing no current because see how all the current density is on the other side. All right. If this was my Amperian loop, that Amperian loop is enclosing current because from this section of the wire. All right. If you had an Amperian loop that was like this, then it's enclosing most of the current because most of the current is flowing through the center, right? If you wanted to calculate the current flowing through an Amperian loop, you use this kind of an integral. Okay, so in other words, if we thought about this like an Amperian loop right here of radius little r, that would tell us the amount of current that flowed through that within that Amperian loop. Okay. Excuse me. So then, so that's an important idea. And then we also have the idea of what's called a line integral. Okay. So a line integral is written, and it's around an Amperian loop. And it's written like this. So it has a circle on it because it's an integral around a loop. B dot dl. Okay. And so, like, let's say we had an Amperian loop that is made up out of straight line segments. So maybe we have an Amperian loop that's like this or something. Okay. So this line segment or this Amperian loop has a number of segments. Okay. And so we're going to call the vector that goes from the beginning of the segment to the end of the segment, we'll call it L. So L1, L2, L3, and L4. All right. And furthermore, there is some magnetic field in the vicinity of there's some magnetic field in the vicinity of this loop. And so maybe on the first segment of the loop, the magnetic field is pointed this way. So we'll call that B1. And then the magnetic field lines change direction. And so on part 2 of the loop, the magnetic field is now pointed in this direction. Something like that. Okay. So what the line integral is it's sort of analogous to the definition of flux, only it's one dimension less. So it's going to be B1 dot L1 plus B2 dot L2 plus dot dot dot, however many segments there are. Okay, so that is called a line integral. This is the line integral of the magnetic field, but you could have any vector field has a line integral. Okay, so so that's a line integral. By far, the most important line integral is going to be a circular loop. Is by far the most important. Okay, so we could think about a circular loop much like we thought of a sphere as a single face that is curved. We're going to think about a circular loop as a single line segment that is curved. Okay, so if you have a circle, the line integral of b dot dl is just going to give you b times 2 pi r, where r is the radius, because the length of going around a circle is 2 pi r. All right. And here we are assuming that that b is parallel to dl, because that's why there's no cosine of theta term in the dot product. All right. So this is going to lead us to Ampere's law. So we have all the ingredients for Ampere's law. So what Ampere's law says is that the line integral of the magnetic field around an Amperian loop, okay, is equal to a constant times the current enclosed by that loop. All right? So this is called Ampere's law. Okay? So let me write it out in words. The line integral of the magnetic field around an Amperian loop. So an Amperian loop is kind of like the magnetic analog of a Gaussian surface, is equal to a constant times the current enclosed by the loop. Okay? Hang on one second, class. I hear a dog doing something stupid. Okay. So that's Ampere's law. So let's apply Ampere's law. All right. So let's do an example. We'll do 2 examples with Ampere's law. And so this first example, we've got 2 currents here. We've got a current I1, all right, that is going out of the page. And then that current is surrounded by another out of the page current that is making like a ring around it. So the total amount of current in this outer ring portion is I2. So that's if we added up all of these not each one, but in total, all of these currents add up to I2. All right? And so what we want to do is we want to use Ampere's law to find the magnitude of the magnetic field as a function of distance. Okay? So basically, we are going to have an Amperian loop that is a circle, and the circular Amperian loop is going to the circular Amperian loop, the radius of that Amperian loop is going to determine how much current is enclosed. So and by the way, I need to give the radius of this. So let's say it goes out to a radius of big R. Okay? So what if my Amperian loop is this size? In that case, the only current that this Amperian loop is enclosing is the current in the center. All right? So in the first case, we have the current enclosed is just I1. Okay, because this Amperian loop is not lassoing both currents. All right? So if we do Ampere's law, and remember, if you have a circular Amperian loop, the left-hand side of Ampere's law, the line integral is going to be b times 2 pi r, okay? Where r is little r, it's the radius of the Amperian loop. So we get b times 2 pi little r equals mu naught I1. And then we can solve for the magnetic field. So we would get b equals mu naught I1 over 2 pi r. That's in region 1, which would be in between the center and this ring of current that's around it. Notice how this is the same as what we got with the Biot-Savart law. Okay, so you might recall that I'm trying to make sort of an analogy with electric fields. Okay, so with electric fields, we started out by doing Coulomb's law, which required integration. And then we went to Gauss's law, and it allowed us to get the electric field in certain symmetrical situations very easily. Okay, so Ampere's law is the same way. You can use the Biot-Savart law, which is a lot more, computationally intensive. But if there is a lot of symmetry, you can use Ampere's law instead and get the answer a lot quicker. So, because remember, we had to do this infinite integral to get the magnetic field from a straight line before. Now we don't. Case 2 would be a case where the Amperian loop is outside of both the central current and then the ring of current around it's out of the page. The ring of current that is going out of the page. Okay, so now this larger loop is enclosing both the inner current and the outer current. All right, so the current enclosed is going to be the sum of those two, which would be I1 plus I2. And so our Ampere's law is going to be the integral of b dot dl equals mu naught times the current enclosed. And so the left-hand side is, again, B times 2 pi r. All right. And the right-hand side is going to be mu naught times I1 plus I2. So that tells us that in the second region, the magnetic field is mu naught times I1 plus I2 over 2 pi r. So if we were to graph magnetic field versus distance from the center, it's going to look like this. It's like a graph of 1 over x. Okay, so it's going to come down from infinity. And then once we hit little r equals big R, then the Amperian loop now starts to enclose more current. So we're going to get a little bump in the magnetic field, and then it will continue to drop. So it's going to kind of look like that. So this bump is caused by the fact that we are enclosing the additional current. Okay? So we're going to do one more example. Okay? So this last example is suppose a wire has J of R equals a constant times R to the 1 power. All right? The wire has radius, let's say 5 meters. Okay? That's a really thick wire. Let's just say C is 1 for simplicity. Okay? C is 1. What is the value? So let's calculate B at R equals 2 meters. Okay? So if we think about it, the wire has a radius of 5 meters, but we don't want the magnetic field all the way at the edge of the wire. We want the magnetic field 2 meters from the center, which is maybe right there. All right? So that means that the radius of my Amperian loop is going to be 2 meters. All right? So there's my Amperian loop, and the current enclosed is going to be the current enclosed within that loop. So what I'm going to do to calculate the current enclosed, it's going to be the integral of J times 2 pi little r dr. And my integral is not going to go from 0 to 5 to the edge of the wire because the Amperian loop only has a radius of 2. So I only want to add up the current out to a radius of 2. So it's going to go from 0 to 2 is my integral. So plugging in J of R equals 1 times R to the 1, we would get integral from 0 to 2 of R times 2 pi R dr. So that's 2 pi times the integral of R squared dr from 0 to 2. And so that this integral is going to give 2 to the third divided by 3. All right. And so this is 2 to the third is 8 times 2, 16 pi over 3 is the current enclosed. All right. Then, if I look at the integral of b dot dl, well, that's going to be b times 2 pi r, where r is the radius of the Amperian loop, which is 2 meters. So I have b times 4 pi, right? Because r is 2, so 2 times 2 is 4 pi. So then, plugging that into Ampere's law, we have b dot dl equals mu naught times the current enclosed. So that says 4 pi b, which is the left-hand side, equals mu naught times 16 pi over 3. Pi cancels out. So it looks like b equals 4/3 mu naught. So that would be 16 pi over 3 times 10 to the minus 7 Tesla. All right. Now, what if I wanted to know, what if I wanted the magnetic field at r equals 7 meters? Well, that r equals 7 is beyond the total radius of the wire. Okay, so my Amperian loop is going to have a radius of 7 meters, but because it's enclosing the entire wire, my limit of integration can't go beyond 5 because the wire stops at 5. So when I'm calculating the current enclosed, my integral would only go from 0 to 5. But when I do my integral of b dot dl, that's going to be b times 2 pi times 7. Because the Amperian loop just is the size that it is. This is the radius of the Amperian loop. Okay? So sort of similar to with Gauss's law problems, when you have a finite charge distribution and you want to calculate the electric field beyond that, the charge enclosed is you only go out to where the charge distribution ends. All right? So that is my lesson for today, and I will see you in the Zoom room.